That's good.
All right, let's see. I got your document here. You want to start at 1?
Yeah.
Okay. All of these all of these first 3 are what is called rational quotients, which usually means they have a numerator and a denominator with variables in both. Okay. Now, the very first thing you want to do whenever you encounter a function like this is to find the vertical asymptote. So let's start with the first one. Hold on a moment. Y equal 3x. I wonder why they made that a capital Y. So also, when you see a rational quotient like this, always think factoring as your first step. Can I factor anything top or bottom?
Yeah, you got x plus 1 and x minus 1.
Now, to get vertical asymptotes are always where what happens?
I forgot.
Where the denominator is 0. Okay, in other words, you can't divide by 0. That's almost like the very first law of mathematics. So when you have a division by a variable, then you have to make sure that denominator cannot be 0. Well, what 2 values make it 0?
-1 and 1.
Yeah, x equal -1 or x equal 1. So those are your 2 vertical asymptotes. Okay, so if I'm going to draw the graph, I'm going to have a vertical asymptote here at +1. I'm going to have a vertical asymptote here at -1. The graph never crosses vertical asymptotes. Might cross horizontal asymptotes, but never vertical asymptotes. About horizontal asymptotes? There any?
Wouldn't it just be 0?
Yeah, y equals 0. In other words, it's always important to remember that asymptotes are the equation of a line. It's not a point. Okay, so just saying 0 isn't really enough, but y equals 0 is the same as the x-axis, and that's the horizontal asymptote you get whenever the power in the denominator is greater than the highest power in the numerator. Okay, so, and let's list that. Horizontal asymptote is y equals 0. Are there any holes?
No.
Okay, let's check for x and y intercepts. I'm going to erase some of this stuff so I can make room. Let's see, we know what our vertical asymptotes are. We know what our horizontal asymptote is. How about a x-intercept? What? No, let's do the easy one first. Let's do a y-intercept. How do you get y-intercepts?
So x equal to 0.
What do you get here?
You just get 0.
Okay. So we know the curve has to go through that point right there at y equals 0. In other words, that's our y-intercept. Okay. Now how do we get x-intercept?
Set y equal to 0.
Correct. So now we have to solve the equation 0 equals 3x over x squared minus 1. What causes that to be 0?
It says 0, correct?
Well, it is x equals 0 is the answer, but one of the key things that's not immediately obvious when you have a rational quotient is that if the rational quotient is equal to 0, then the numerator has to be 0. We don't care what this denominator is. If this whole thing is to be equal to 0, well then that has to be 0. The only way you get a rational quotient to be 0 is if the numerator is 0. So that means my x-intercept is right there. Well, that's helpful. At least I know I now have a point that this thing goes through. Now, whenever you have dual vertical asymptotes like this, okay, the equation, the graph of it, is hyperbolic. Again, let me erase this. We know it's going to look, you know what I mean by hyperbolic?
Yeah.
Means that part of the graph, it approaches the vertical asymptote and the horizontal asymptote. And then typically, the other half of the hyperbola is down there. Now, I say typically because sometimes if you have a negative sign, if we put a negative in front of that 3x, then I'm not going to be in the first and the fourth quadrant. I'm going to be in the second or the third and the sixth. In other words, you have to make sure you're in the right spots here. In other words, here's the two possibilities. I'm either like that or I'm the black. Let's wait for a second to talk what happens in the middle, in between the vertical asymptotes. But how can I tell whether the black is correct or the red is correct?
By plugging in points.
Yeah, what's a good point to plug in?
1.
Problem with 1 is it creates division by 0. That doesn't really help. Pick a point.
2 or 3.
2. In other words, pick a whole number that's close to 1. And when you plug in 2, what number do you get for y?
If you plug in 2, you get 6/5.
6 over 3, right? Plug in 2 for x.
Yeah.
Plug in
2
for x, you get 6 over 4 minus 1. So that's 6 over 3. Well, what that tells you is that when I am to the right of that right vertical asymptote, my y is positive. It's 2. It's not negative. In other words, if it was the red curve, it would have to be negative. So immediately, I now know that I got the right graph. The red is not correct, the black is correct. Okay? Still have to figure out what's going on in the middle. Now, there's 2 possibilities for the middle, generally, with these. Almost everyone you're going to get, there's going to be 2 possibilities. One possibility is where it does that. The other possibility is where it doesn't get all the way up to the x-axis, it turns around and it comes back down like that. The fact that we found an x-intercept right there means it's not the red, right?
Yep.
In other words, I know my curve has to go through that x-intercept. Well, the red doesn't do that. So there's my graph. Now, let's talk about something else. This isn't 100% true, but I found it to be 99% true. If you look at this function and you go from right to left, well, notice that the black curve approaches positive infinity on the right side of that asymptote, right?
Mm-hmm.
On the other side of the asymptote, it comes up from negative infinity. As we approach the left asymptote, we're going to positive infinity. On the other side of the asymptote, we come up from negative infinity. And that's very typical. In other words, if the graph would have looked, in other words, let's say we didn't have an x-intercept and I decided that in between the curve that the graph looks like this. Well, that's not a typical hyperbolic function. In other words, it works for the right asymptote, but on the left asymptote, I'm going down to negative infinity on the red, and I'm coming up from negative infinity. So a proper curve here probably would be this one if we did not have an x-intercept. I saw one the other day, and this was exactly how it looked. Notice again that on the right side, on the right side of the asymptote, I'm headed towards positive infinity. On the other side, coming up from negative infinity. On this side, coming up from negative infinity. On the other side, going from positive infinity. So kind of keep that in mind, and that can be very helpful. And the only thing we really needed to draw this graph was the asymptotes and x or y intercepts. We know it's not the red. Let me erase that before I confuse you. And that's black is not there either. We know that it has to go through that point. So it looks like this. And you could put that, it says no calculator, so let's go on. You can't even check, I presume, if you're taking a test. You just have to go with this. Okay. Let's look at number 2. If you don't have any questions on number 1. What's the first step in order to graph this without a calculator?
Find the vertical and horizontal asymptote.
Where's the vertical asymptote?
1.
Vertical asymptotes are always where the denominator is 0.
So -3.
And there's a huge difference between the denominator being 0 and the numerator being 0. If I say what is 0 divided by 7, that's 0. But if I say what is 7 divided by 0, that's actually infinity. And in fact, they'll usually say that does not exist. Okay? So there's a gigantic difference between 0 and infinity. They're, almost on opposite sides of the number line. So don't mistake dividing into 0 with dividing by 0. So the vertical asymptote is always wherever the denominator is 0. Where's the horizontal asymptote?
Wouldn't it be at 1?
Yeah, when the highest power of the variable is the same in the numerator and the denominator, then the horizontal asymptote, which is always an equation defined by y, equals, is the ratio of their coefficients, 1 over 1. Okay? Now we can draw that thing. We got a vertical asymptote right there. Got a horizontal asymptote right there. And this is pretty typical of hyperbolic functions, is you end up with a grid. A grid like 4 quadrants. Okay? And again, graphing this thing is pretty straightforward. There's no middle this time. So the graph is either that or the red. Which one is it? How do you figure it out?
We can find the y-intercept.
We may not need that, but you're correct. No, not necessarily. Well, Here's an easier way. What did we do last time?
Plug something in.
Okay, what's a good number to plug in? Makes everything easy.
0.
Okay, what is y when x is 0?
1/3.
Ah, that's below that horizontal asymptote, right? There's 1/3. In other words, if the answer would have come out to be greater than 1, we'd have known the black is the correct. Well, the answer didn't. The answer clearly puts us in this fourth quadrant. So now I know how to graph it. It's not the red, or excuse me, it's not the black, it's the red. And, you know, if your life depended on it, you might want to put in a number to the left of -3 just to make sure we're in the right spot. Now let's put in -4. -4 gives us -3 over -1, which is a +3.
And that goes over, so that would work.
Right there. Okay. So, yeah, so our red is correct. All right. So far we haven't had any holes. It said state the domain and range of each graph. I forgot to do that. We may have to go back and do that. But are you good with domain and range? What does domain mean? What's the domain of the first function? Let's while we're thinking of it, yeah.
Would it just be everything minus the vertical asymptote?
The vertical asymptotes were at ±1. So it's all real numbers except for x cannot be equal to ±1. Now, do they make you give domains and ranges in interval notation?
Yeah, they do.
Okay, what's the interval notation for the domain on number 1? I'll give you a hint. It's the first domain. If it can't be -1, what can it be? Always start from -infinity on your interval notation.
It would be -infinity to -1.
Bracket or parentheses?
Parentheses.
Because it cannot be -1. Okay, in combination with?
-1 to 1.
Combination with?
1 to infinity.
Okay. Now the range on number 1. If you'll remember what the graph looked like on number 1, it kind of looked like this. Hold on, excuse me. Looked like this. And in the middle we had something like that, right? We have vertical asymptotes here and here. Read the range off that function from the graph.
The range would be, would it just be all real numbers?
Yes. In other words, the range can come entirely from that part right there. That's -infinity to +infinity. Now, if we back up and if we didn't have an x-intercept and the graph looked more like this, now what's the range?
It would be -infinity to 0, 0 to
Not 0, but to whatever that value is. Well, it turns out that that value you can't figure out without calculus. You could if you had calculus, but you need to put that into a calculator to figure out what the y value is there. And that's critical for the range, because the range cannot be greater than this and less than 0. In other words, there's a small area here that is not in your range. See why?
Mm-hmm.
In other words, y can never be 0 in this picture here. In fact, y can't even be -1 probably, because -1 is in that little area there also. All right. Let's go back to number 2. What's the domain?
That would be negative infinity to -3, -3 to positive infinity.
Good. What's the range?
The range would be negative infinity to 1 to positive infinity.
Okay, cool. Now let's look at number 3. What's the very first thing I'm going to do when I see a problem like number 3?
Factor.
Okay, factor the numerator. You want to factor anything you can, but in this case, the numerator is the only one you can actually factor. How does it factor?
It factors into, it would be x plus 2 and x plus 1.
Now, normally we'd look at that denominator and we would say there's a vertical asymptote of -1, right?
Mm-hmm.
But not in this case. In other words, the first thing you do is you cross out common factors. And so this function ends up being x plus 2, not even hyperbolic. But here's the kicker. The domain restriction of the original function is x cannot be equal to -1, correct? That does not go away. In other words, there's your answer, and what that means is you have a hole at -1. So how do I graph this? Well, it's a straight linear function, x plus 2. How do you graph y equal x plus 2?
Just go up to and make just a x equals y.
Start with the y-intercept at 2, because that's what that 2 is b. And then what's the slope?
Just 1.
Okay, so I go up 1 and right 1. Now I have 2 points. I can connect the 2 points. But there's one further thing I have to do. I have to go to -1 and put a hole right there. What that means is that x can still not be -1 ever. Would violate the domain, even though the final function doesn't look like it. In other words, if you looked only at this final function, x plus 2, it doesn't look like there's any domain restrictions.
Mm-hmm.
But there are. What's the range? So the domain is all real numbers except x equal -1.
Okay.
What's the range?
It would be negative infinity to -1, and then -1 to positive infinity.
Yeah, not -1. This is +1. In other words, that's the only thing y cannot be equal to. And if you plug in this -1 that you're not ever supposed to use into this final function, you get 1, not -1. Okay, in other words, that value right there is a y of 1. So the range is negative infinity to 1 in combination with 1 to positive infinity. You see why?
Yep.
Okay. Believe it or not, at Chatfield, they teach this. I sat in with the teacher and watched her do it, and then I had other students that did it. And they try to tell you that there's a value at x equal -1.
Wow, really?
There is not. No. The very first thing about holes is that x cannot be -1. It is not part of the domain. And if something isn't part of the domain, then you don't go figuring out what y is at that point. So this is everything about that picture. And you notice on this one, we didn't really need x and y intercepts because there really was no question about how to draw the graph. Once we ended up with x plus 2 as our function, well, that's real easy. That's just a linear straight line curve. And the only thing that was important about it was there was a hole at x equal minus 1.
Mm-hmm.
And that's how you get holes. What would have been a vertical asymptote turns into a hole if it can be canceled with a factor in the numerator. It's as straightforward as that. That's the only time. Okay? And oddly enough, if you put this function into your calculator, it will not show you that hole. If I put it into Wolfram Alpha, it would not show me that hole. Why not? Because that hole is infinitesimally small. It occurs where x is equal to minus 1 only. Well, that's 1 point on a number line that has an infinite number of points between 0 and minus 2. So the point x equal minus 1 is, you don't really see it as a hole on the graph. The graph's going to look at it, it doesn't have the ability to draw a circle at a point that is fractionally wide.
Mm-hmm.
So it won't show it on the graph. Maybe what you don't use an Inspire, do you?
No, I just use a TI-84.
No, it doesn't show it, the TI-84. It's possible that some of these new graphing calculators might show the hole. In other words, they might know enough about the math to know that there's a hole and they would put it in there. But typically, the old graphing calculators will graph it exactly as they see it. And they see a hole and they put a hole in there, but by the time you see it on your graphing calculator, you can't see that there's a hole there. It's too small to see. All right. Sketch this piecewise function. Piecewise functions, for some reason, give people a lot of trouble, but they shouldn't. Okay? Here's where you want to start when you're looking at a piecewise function. You see where my cursor's pointed?
Yeah.
Okay, I'm going to draw a dotted line here, even though I don't typically draw a dotted line. I'm just going to do it for illustration purposes. That's at 1. So what this is saying is that the first place I have to graph is in this region of the domain. And that's the way to look at these. In other words, everywhere where you see my horizontal scribbly line, I'm going to graph the function 3x minus 4. Okay, well that's a pretty easy function to graph. How do I graph that? Where do I start?
You find the y-intercept is at -4.
Okay.
And it has a stretch factor of 3.
It's got a slope of 3. Don't really think of it as being a stretch factor. Not in this case. It's actually a misnomer. Its slope is 3. So I got 1 point on the graph right there. So all I have to do is go up 3 and right 1. Well, up 3 and right 1 puts me right there. Okay. And so here's my graph. Should this be a closed dot or an open dot?
Open.
Correct. I'm going to eliminate that dotted line merely because you don't usually put the dotted line there. Not with
probably a lot for sketching though.
Well, it's useful. The next domain that I'm dealing with is what?
1 through 4.
Okay. So there's 1 and 4, and this time I'm going to be graphing in this area here. What's the graph in that area according to the function?
It just says 2, so should it just be a straight line?
Horizontal line. Make sure you know the difference between horizontal lines are y equals a number, vertical lines are x equals a number. Well, this says it's a function, so you know you're not going to have any vertical lines here, otherwise it wouldn't be a function. So the horizontal line at y equal 2 goes between that point and that point. Open or closed on which ends?
Closed on 1 and open on 4.
Yeah. And then finally, the last part of the domain is everything to the right of that.
And that's just 5.
Correct. And it's closed right there, and that goes on to infinity. So that's how you do piecewise functions. Now, let me just talk to you about a more difficult piecewise function, because you would do it differently than this. Let's say x was less than -1, was our top part here. Okay, I just want to show you this, because if you get it on a test, it might stump you if you weren't aware of how to do it. In other words, let's make that domain x is less than -1. In other words, this area. Okay? With me?
Uh-huh.
How would I graph the function y equals 3x minus 4, because it doesn't go through the y-intercept? Where do I start?
Would you just start graphing it out and then just erase the rest?
The way I used to do it. That is the way I used to do it. I would do it like this. And then the part that didn't belong, I would go in and I would erase it. And then I would be left with that. That's not the way to do it. Okay, for one thing, it's just extra graphs. Piecewise has enough lines on there anyway. You don't want extra lines that you have to erase. The best way to do it is to take this part of the domain, which is x equal -1, plug it into the function, you get y equals -7, right? Right?
Right.
-1 times 3 is -3, -4 is -7. So that's where I start, is at y -7. Now I don't have to go to the y-intercept. I still have a slope of 3, but I can go down 3, left 1. So I get my line without having to use the y-intercept. And that was what I'm trying to point out, is it won't always be convenient to use the y-intercept. And if you have functions that are quadratic in nature, well, then you won't really be able to use the y-intercept, and you'll have to do it this way. But always take whatever this value is right there and plug it into your function, and that's your starting point. Just like the y-intercept would normally be your starting point, what you're really doing is plugging in 0 for x, and you're figuring out what y is, and that gives you the y-intercept. But this particular piecewise function doesn't go to the y-intercept, so I can't do it that way. So I have to do it this way. All right.
Okay.
The domain of number 5. You can give it to me in shorthand instead of interval notation. I know you know how to do interval notation now.
Would it be all real numbers except for 4?
Correct. Number 6, what's the first thing we're going to do?
Factor.
Okay, factor the bottom.
You have x plus 4 and x plus 1.
A little hint here is whatever this factor in this side's going to be, there's probably going to be one of these factors. So if factoring gives you a little bit of trouble, you almost know what one of the factors has to be. It has to be x plus 1, because this is going to be a problem where we're going to get a hole. Remember, you create holes. In other words, we do not have two vertical asymptotes here. What's the domain of this function? That's all they ask for.
Shouldn't it be x minus 1? No. Sorry.
All reals except what?
All reals except -1 and +1?
No, the denominator is the only thing that matters for domain in this case.
Oh, -1 and -4 then.
Yeah. And the fact that this creates a hole, in other words, the fact that that happens, doesn't really affect the domain. In other words, this numerator might be x plus 2, and I would still have the same domain, all reals except -1 and -4. So by making it x plus 1, and I could cancel it out, remember that that hole sticks with the domain, so it doesn't change the domain, whether I can cancel it or not. The domain is usually restricted by the denominator, sometimes by the numerator, but in these kind of problems, it's the denominator that restricts the domain. If I had y equals square root of x, different story. Now the domain is affected by the radical sign. In other words, x's have to be positive or 0. All right, what are the coordinates of the hole on number 7? Well, let's start by factoring what we can factor. What's the numerator?
I don't know. I'm really sure how to factor that, to be honest.
Make a greatest common factor out of that. Always, yeah. That's always your first thing to look for.
Oh, so it would just be x and then parentheses x minus 1.
Yeah, and again, look for the x minus 1. You know it's probably going to be there, right?
Uh-huh.
Okay. So in this case, I do have a hole. In other words, this function is actually y equal to x, but there's a hole where?
At +1.
Okay. What are the coordinates of that hole? In other words, the function looks like this. That's y equal x. You said there was a hole at +1, so the hole is right there. What are the coordinates of that hole?
1, 1.
Yeah, 1, 1, which means y can never be 1 and x can never be 1.
Okay.
Okay. Slant asymptotes. Hold on. There's 3 situations. There's this situation. What's the horizontal asymptote?
1/3.
2/3.
-1/3.
2/3.
Oh.
It's all, in other words, in this situation, the maximum power of the x is 1 in both top and bottom. Even if I make that x squared and that x squared, still have a horizontal asymptote at 2/3. Okay, you with me?
Okay.
That's one situation where they're equal. The other situation is where the bottom is bigger than the top, like this. Okay. What's the horizontal asymptote in the middle function?
It would be 0.
Y equals 0. It's always equal to 0 if the bottom has a higher degree than the top. Okay? Now there's one other situation, and that's where the top is exactly 1 bigger than the bottom. And something like that. When you have this situation, you're going to produce not a horizontal asymptote, but a slant asymptote. And you get it by doing the division. In other words, you do the long division. So in this problem where they say, what's the slant asymptote? I know that the bottom is going to be 1 degree less than the top, otherwise there wouldn't be a slant asymptote. And you get it by doing the division. This is what I mean by doing the long division. Okay? And you may not be used to doing long division on polynomials like this, but it's really not hard. How do you do that long division? It's the first thing.
When do you find it? I'm not very sure, to be honest.
It doesn't factor. Notice that that won't factor. There's only 2 factors for 7. That's 7 and 1. Neither one of them produce that as a middle term. So after, even if it did factor, I'm not sure we wouldn't want to do the division. I'll show you why. The way you do the division, you still there, Jake?
Yeah. Yeah, sorry.
The way you do the division is you take that term and divide it into that term. What do you get?
X.
Then you take this and multiply it by both. So I get x squared minus x. And then with long division, you're always subtracting. So this goes to 0. This 3x minus a minus x goes to plus 4x. Bring down the 7. Repeat. Exactly the same process. X goes into 4x 4 times. Now multiply the 4 by 4x minus 4. Now we get a remainder of minus 11. So we have a remainder of minus 11, and your remainder is always divided by your divisor. So that's the answer. The equation of the slant asymptote is this linear function, always. You don't care about the remainder. I mean, you care about the remainder in the sense that it tells you you're going to have a vertical asymptote at 1, but we knew that from looking at the original function. We know there's a vertical asymptote at x equal 1. The question is, where's the slant asymptote? Well, after you do the division, take your linear term, and that is the slant asymptote, regardless of what the remainder is.
Mm-hmm.
You could actually throw that away in terms of graphing it. I don't need it. I already know I have a vertical asymptote at x equal 1, and I have a slant asymptote that is the line y equal x plus 4. So if I'm going to graph that, y equal x plus 4, it's like that. And I have a vertical asymptote at x equal 1. So my grid looks like that. It's not just horizontal and vertical lines. It's usually a vertical asymptote with a slant asymptote. Okay? Mm-hmm. Now my graph, I got some choices on. Again, it's hyperbolic. So I know that the definition of a slant asymptote is this is what the function is going to approach as x goes to plus infinity and minus infinity. So, and I know that it always approaches the vertical asymptote, so it looks something like that, and the other half of it would be that. But there's another choice here. Again, as always, it could be in these 2 quadrants. So
would you just put 0?
Well, one way to determine which one you have is to figure out what the x-intercepts are. Okay, although that's even, yeah, if you figure out the x-intercept, you'll know whether you're to the right or the left of this vertical asymptote. I know the vertical asymptote's at x equal 1, right?
Yep.
I'll plug in 2 into the function. What do you get?
Plug in 2. You should get 3.
No, if you plug in 2 to this number 7 here, that's the one we're working with, right? No, excuse me, sorry. Number 8. If I plug in 2, I get 4 plus 6 is 10 minus 7, I get 3 over 1. So when I plug in 2, which is right there on the x-axis, I get 3. Well, I can't tell. That point there could be 3, that point there could be 3. So that still doesn't help with determining which line I get. What's another way that, how about the y-intercept? If I can determine that the y-intercept is above this point, I know where that point is, that's at 4. So that's a better way to tell. In other words, if the black curve is my black curve, if that's my correct curve, then the y-intercept's going to come less than 4. If the red curve is correct, the y-intercept's going to come greater than 4, right?
Right.
Plug in 0, where's the y-intercept?
You'll be at 7.
Plug in 0, the numerator is 0. Oh, again, I screwed up. Yeah, 7. At x equals 0, the y-intercept is 7. That tells me the red curve is my proper curve.
Mm-hmm.
In other words, there's all you can't really tell by looking at the function, at least I can't. Maybe there's a good way to do it, but I've never been able to tell without plugging in a few of these points. And so my final curve is this red curve here. And if I were to look for some x-intercepts, I would find the points where it crosses the x-axis. But it didn't ask you to do all of that stuff. The only thing it really asked you to do is find the slant asymptote. And we did that. The slant asymptote was y equal x plus 4. That's the answer.
Mm-hmm.
Okay, all right. Let's see, we got time for another one of these slant asymptotes. The very first moment you find the slant asymptote, you know it's a long division problem, right?
Yeah.
All right, this one's a little different because it is missing an x term. And you have to always have a spot for all of your possible powers of x. So what you do is the numerator is missing an x term also. So you have 0x minus 5, and here you put a dummy variable right there also. So if I'm dividing something by x squared plus 1, I'm really going to divide this polynomial by this whole polynomial. Okay, what's first step?
Would the top just be x?
Correct.
Or stop?
Now multiply that x by all 3 terms. Now we put in these dummy variables so everything will line up. That's why we do it. Okay.
Would it be x cubed plus 0x cubed plus x?
Plus 0x squared, right? In other words, x times 0x is 0x squared, just to be proper, plus x, subtract.
And you'll get x squared minus x.
Bring down your remainder, stir and repeat. What's the next term in the quotient?
X squared again, so wouldn't it just be 1?
plus 1. And that's the equation of your slant asymptote. Y equal x plus 1. That's all they ask for. We're done. The only thing different about that problem was we had to put in dummy variables both into the divisor and the dividend. And you always have to allow for every power of x. In other words, if my original function was x to the fourth plus 1, well then I need x to the fourth plus 0, x to the third plus 0, x squared plus 0, x plus 1. You know, you see what I'm saying?
Yeah.
Okay. Quite a bit of material here.
Yeah.
Which we're obviously probably not going to get to all tonight. Do you have a test coming up on this?
Yeah, I have it tomorrow.
Oh, you do have the test tomorrow. Okay. Number 10 looks fairly straightforward. Gives you a function, y equals something, and y is the amount of food consumed, x is the amount of food supplied. Okay? The horizontal asymptote of that function. Y equal what?
It would be y equals
ratio of the coefficients. In other words, because the maximum power in the numerator is x to the 1, and in the denominator is x to the 1, then this ratio is your horizontal asymptote. Okay? And what does that mean? In other words, that horizontal asymptote is a line kind of like that. What's the real world meaning of horizontal asymptote?
Where it plateaus.
It's what happens as x goes to infinity. It's what the function is going to approach. Okay? So the function I will draw in red, and I'm just going to guess. There's also a vertical asymptote here at some negative number where that thing is equal to -1. So I'm just going to guess a vertical asymptote right there. Okay. And now if the graph is hyperbolic in nature and x has to be greater than 0, so I wouldn't have this part here. I would just have the part from here to there going all the way out. So what that says is that as x goes to infinity, the function goes to that horizontal asymptote, whatever that ratio is, 1/4 or something like that. And that's the definition of horizontal asymptote. It's in behavior. It's what happens. In behavior means as x goes to positive infinity or negative infinity. Okay? So even if x could go to positive and negative infinity, well, either side it approaches this horizontal asymptote, right? For this particular problem, they said x has to be greater than 0, so we're going to get rid of that part of it, and we're going to get rid of that part of it, and what we end up with is that. But the real life meaning of horizontal asymptote in this problem is what's going to happen as x goes to positive infinity. Well, we can see what happens. The function goes to whatever this horizontal asymptote is. Goes to that. All right. Let's see. Find and explain the meaning of vertical asymptote. This is a cost function where P is the percentage of the population. Well, vertical asymptotes come from what?
The denominator.
Where's the vertical asymptote on number 11?
100.
P equals 100.
Wouldn't that just be because it's a percentage, so it's out of 100?
No, it's, well, I don't even know what P means at this point. I'm just looking at the function. The only thing I know is that P cannot be 100. So therefore, your vertical asymptote is not 100. Your vertical asymptote is x equals 100. Okay? And one thing about vertical asymptotes is they can never be crossed. So we got the P, it's not x, it's P. There's a vertical asymptote right there. It's also a horizontal asymptote that's the ratio of the coefficients, which is huge. It's negative 25,000, right? So there's a horizontal asymptote down there at minus 25,000. What's the meaning of the vertical asymptote? And our graph, I'll graph it in red, it most likely is going to be hyperbolic. And I didn't make this thing big enough. Here, let me draw it just a little bit bigger. So it's going to approach both asymptotes. What's the meaning of the vertical asymptote?
I was thinking because it's a percentage.
Nope, doesn't have anything to do with that.
I have no idea.
It means P can never be what that vertical asymptote is.
Mm-hmm.
So P cannot be 100. So in this case, since P is the percentage of the population, you can never have 100% of the population for this particular word problem. And that's what it means, is that the variable cannot be the vertical asymptote. So in this case, P cannot ever be 100%. Why? I guess we could figure it out. In other words, you can't supply recycling bins to all, you can't do it to 100% of the population. The cost would be enormous. Notice what happens from my graph as we approach the vertical asymptote. Cost goes to positive infinity as we approach it from the right.
Mm-hmm.
So the cost becomes infinite if we were to try to cover or supply recycling bins to the entire population, 100% of the population. And therefore, that's why P really can't equal 100, is because if you let P equal 100, this cost becomes basically infinite.
Mm-hmm.
Whenever you divide by 0, you're looking at it either in negative infinity or positive infinity. And they just say it doesn't exist. But the reality is that it's infinitely large. And that's why the function is like it is. And why P can never be 100 is because the cost would be infinite.
Mm-hmm.
Well, that's probably a good place to stop, I guess, huh?
Yeah, thank you. This helped a lot.
You're welcome. I'm sorry we didn't get through all of it.
Oh, no, it's fine. You covered the most important stuff for me. So.
I was going to say, if you like, give me a little break here and we can do more tonight if you need to, but I'll leave that up to you.
I'll go ask my parents and see if that's okay.
I don't have anything else scheduled tonight, so just give me a break. In other words, I wouldn't want to do it right now. My voice is hoarse.
Okay.
But I could certainly do it a little bit later from tonight. Okay? All right, Jay. Just call me if you need more tonight. Otherwise, I'll talk to you next time. Good luck on your test.
All right. Thank you.
All right. Bye-bye.
Bye.